Okay, let us continue. So maybe this one you said
okay, maybe I should say this is the second part, right?
Right.
Of homotopical
use
characterization. So Aziz will continue on the characterization.
Yeah.
Okay.
No, I wanted to ask only that this is good.
Okay.
This is good because yes, last time I remember you said this.
Wait. Okay. So I need to choose this. Sorry. I think the red is good.
Red is good, like this, for example.
Yeah, I think it's good.
Good. Yeah. Okay. When it's not, you can. Okay, let me remind you what we did last time. Actually, what we said, if we have, let's say, we have a scenario, simplicial scenario, the general x, okay, and here m outcome. And what we said, like if we have some simplicial distribution, such that when we down here to the nerve, we said that there is a map last time from delta Zm to the nerve of Zm, like this is play the rule of the okay, some like for the dual of the cone, the path space for the nerve. Okay, so there is a map. So let's call it, I think I called it pi. So this is d of pi. So if after doing like this, we will get deterministic distribution. That means a distribution that coming by using this delta. Yeah, this is v now. We use the red. Yeah, this is v. So if we have, if there is such a phi that not null homotopic, then that means that P is strongly contextual. Okay, that means. Okay, now what about the inverse direction? The inverse direction is that true, but because actually it's strong, like to be like on the whole x, it's strong to be deterministic on the nerve. Like if we down to the nerve to be deterministic in the whole x is strong, so it's enough to be for subspace. Like if we have some subspace C prime such that this is deterministic and there is a map like this, okay, such that this is not null homotopic. So we have some deterministic that the diagram commute. If we have something like this, then it's enough to be like, okay, this is something more general, right? Yeah, I will write like if there is subspace of x and phi from this to the nerve of n such that the diagram or such that diagram 1, this is diagram 1, I mean, commutes. That means the restricting of P on X, if I restrict P on this and down to the nerve, this will be deterministic, but not any deterministic that come from not null homotopic map, okay? Such that, and maybe I'm free, and also we should add this, that this is not null homotopic, such that the diagram commute, then P is strongly contextual. Okay, this is a statement. But of course, here to be not null homotopic, here it's enough to be a circle. If one think about the nerve, okay, to be not null homotopic is a circle. So if it's a circle, let's call this C. Yeah, I mean this is a circle. Okay, so it's enough to say here there is a circle. The same. It will be the same because. So this is the statement. And now after make it something like weaker, softer, we make it softer by adding like, okay, it's enough to be for subs like this. We can ask now if it's if and only if. And also it's not if and only if, but like it's in one direction, but it's true this is what we will do now in this, because this we proved already, but the converse direction is true when in the simplest case, when x is one dimensional and m is equal to 2, like we have two outcomes like z2 when we work on z2. This is true, the convex direction is true. That means that every strongly contextual, if we start from strongly contextual, it should have some, it's coming from some file like this, okay, some map like this, that not null homotopic and diagram commute. Okay, so
for the first iteration you don't have any dimensional restriction.
Yeah, for first, no, not on M and not on X. Yeah, it's true always. Yeah, the first direction is true always. It depends on what we said last time. Okay, now in order to prove the second direction, we should use what calls compository. So let's talk about this. Okay, this is good. Maybe not good. Yeah, not that good. Yeah, okay. We'll talk about compository. Okay, compository is it's appeared first time like introduced by Flory and Fritz in their paper in something 2011 or or something like this. So what is compository? Actually, it's a simplicial. Compository is a simplicial set X with higher compositions. Like higher structure of composition, because it's plus like higher composition plus some axiom, okay, certain axioms, like this composition satisfies certain axiom. Okay, maybe I should write this satisfy. Satisfy certain axiom. Okay, this is what it's mean. Okay, what it's really in details. What does that mean? What we mean by higher composition? What we mean by higher composition? Like if we are here in X, what is X simplicial sets? Okay, there is degree. Like if we are here in X n, degree n, this said, and here in X m. So then, and I go to the, like there is a map using the faces map. We can go to the end, like everyone to the end of, let me maybe give you example. It will be better. Like if I, for example, in X3, so every like thing we can, like as a pyramid, okay? Pyramid. And then is we going, for example, to X1 to the end. Like I have here pyramid. This is the end. And here it send me like this one, send to the end of this to this. Yeah, to this. Yeah, so this, let's call it S1. Okay, I mean the end or terminal, maybe T1 is the terminal T1. Okay, if I write T2, so I mean like this one, T2. Yeah, I mean this one. It's going to, yeah, it's depends on the dimension. So there is such a map, and there is a map to the beginning, like SK here to XK. Of course, K it's in dimension less than n. Okay. Like here is the example, x3 to x1. And for example, here we go from x2 to x1, the beginning of x1, like it's this one, I have something in x2, like I can think this one, and to the beginning of this, like 0, 1 to this one. Yeah, this is this one. Okay, so this is S1, it's called, and this is T1. Yeah. So in general, we have like this TK and SK. Okay, these two maps. And if we have these two maps, like every two like that coincide here, like I have some pyramid, something in x3 and something in x2, but they are the end of this is equal to the beginning of this. Okay, the end of this is equal. This one is equal to this if they are coincide. What? SK, it's, I mean, maybe it's the opposite. I use the opposite, TK here. Yeah, okay, I use the opposite there in order not to confuse. Of faces maps. No, of faces maps. Yeah. What?
So S looks like degeneracy. I think it's confused.
It's confused. Maybe let me, right. Let me use another word. Yeah, I mean here, T terminal, let's say the end of the, and that's what is initial I. I is good, I don't. I initial. Yeah, right, you are right. I1. It's going to the initial one, like the first one, in order. Like here I applied D2, by the way. Here I applied D2. Here I applied what I applied. I applied D0 twice. D0, D0. Yeah? If I apply D0, I will go into this, and apply again D0. Yeah, D0 twice, here D2. You apply D, like in order to get the first one, you apply the end one, like dn minus 1 until d, I don't know, yeah, this in order to t or I of something. And t of something, the terminal, you apply d0 many times, like this. Yeah.
Okay. But there are so many maps, right?
Yeah, there is so many. Yeah. TK in general, this is general. Here is example. Yeah.
You don't take any specific base map.
No, but T, how we are by taking the D zeros here, by taking the D of the end, D2, the D of the end composition. Yeah, of course, yeah, of course there is, yeah, of course. For example, this can be like D of this, D1, and then applying something D0, yeah, right, of course. Yeah, and here if I have some object in the in the limit of the pullback of this, like that mean, what is that mean? That means someone from here and someone from here that coincide, okay? Then actually what it means, the composition that we have a map from this to x m plus n minus k. Like in this case, for example, because this and this coincide, like the end of this and the beginning of this coincide, yeah, then I will get something where this is 3-dimensional and this in 2-dimensional, and they coincide in something 1-dimensional. So they will going to something, they will give me something in where in x 3 plus 2 minus 1. So in x4. Yeah, in x4 they will give me something. Okay, it's hard for me to write a picture. Let me give you some example like less dimensional, so as you can understand. Like this is a kind of composition. So we have such operation like this for every, like for every situation like this. I taking xn here, xn, for every situation we have such a map. Okay, like we have many maps like this.
Yes, but the last map you draw, is it unique?
Yeah, there is a map like this, unique. Yeah. I know what you know about maybe quasi categories. So that's what you ask. Is unique? Maybe, yeah. No, it's unique. It's there is operation like this. No, it's unique. It's a map, like definition. Like let me start with the simple examples. The simple examples when we have x1 to x0. D0, one of them. Which one we take the terminal? D1, T, it's, yeah, D0. Like this is the T, D0, and T, and what we call it, I0, it's D1. Okay? So what we have actually here, how it looks like here in Xn, it looks like where there is H in X1, and there is another H that they coincide. The end of this is, yeah. And what it gives you actually, it's we mean there is a map here. This is the composition map. This is the composition. Okay, of course we need here some. Okay, all the composition like this. This is specific composition. Like this is a composition for it's corresponding to this ones, to T and I. But anyway, like all of them, we will write like this. So there is a composition to X2, right? 1 plus 1 minus 0. Like by this, if you are here, this is the whole simplicial. Okay, so, so we take like this is sigma 1, sigma 2. If we take sigma 1, sigma 2 here that coincide in some way, like D0 of this, if we apply D0 of this or D1 of this, maybe it's the opposite, like, okay, D, just a minute, D1 of sigma 2, right, yeah. And this is the same, then it's give you, like this both, give you the composition of this both. It will be something here. Yeah. Something in here, what it's mean, like we can feel it. Like if there is something here. Yeah. Okay. Okay. But of course, maybe we can now, maybe one can say, I know one of the axioms that you're talking about. One of the axioms, of course, will ask that if I'm taking the D, okay, this is 0, 1, 2. Of course, one of the axiom, like this is a new simplex here, right? So one of the axiom will be that D2 of this simplex, the new simplex, what is this? D2 of this simplex, of this new simplex, will be D2 sigma 1. And D0 of this simplex is sigma 2. What I said, there is a operation like this, okay, but I didn't say that what is the property. But of course, one of the property, in order to be really composition or gluing or what you want to say, okay, it's one of the, it's like this. Of course, there is general. I will not going to write the general axioms. You will see this, but I want you to feel, when you read it, to feel what it means, axiom. So one of the axiom will be something like this in general, okay, to have this in order to be really composition, right? Really, we have the composition of this. But yeah, okay, so the composition of this give me something higher, like I can feel. This is kind of composition uniquely, like you okay, every compositor have his compositions, okay? Like it's not that I, like, yeah, like this. Okay, and maybe another example, if we have, like, okay, maybe in order not to write like this, if we have this, and we have here triangle, and let's say the end of this, we see the end of this one, this is sigma 1, and this is now is sigma 2, yeah, and we see that the end of sigma 1 it's equal to sigma 2. So what they said me, there is something that we can feel it, okay, like there is this going to, by the composition of this will be what? Pyramid, right? Because it's this 1 plus 2 minus 0, so 3 will be pyramid, like it will be, so it will be something like this, like something like this. Sorry. Yeah, that have, of course, in this side, sigma 1 it's in this side and sigma 2 in this side, but it's complete like pyramid, it's filled. Yeah, this is what we have.
Are you going to the definition for what? It's a set with high composition.
With many composition like this. This is a composition. Like every situation you have like this.
Special sets.
Example, you mean, for specific example?
I think maybe the definition is not clear. So the definition is compository is a simplicial set with those circle maps. So you have those maps are givens.
Those map givens, yeah, as a part, yeah. Like this is what I mean by higher composition. There is money like this, like every situation like this. For every, I can write here for every x, like for every something like this. When you know what I mean by tk and the ik, for every something like this, we have composition. This composition from the xn, xm, xk to xn plus m minus k. Yeah, this is what I mean. Yeah, for every we have so we have many compositions. For any situation like this, when you're going like this by d zeros, by many d zeros, and here by many d1 until you going here by many tn, I don't know, dm, maybe dm minus 1, something like that. Yeah, this is the initial and the end. If they are the same, you take some simplex, they are the same, then you have, there is some operation that, okay, give you new simplex. You apply this operation and give you new simplex. Okay, so you have many operation, many function like this, many compositions. There's, yeah, many infinity compositions. There is many, but of course this composition have some properties. Okay, one of the properties we see like this, what I tried. Yeah, you can find it's like general case, but okay, let's like no, like this one, it will be also like when we take this one, it will be sigma 1. It's when we take this one, it will be sigma 2. Like it's remember where it came from. It's not like it's feeling that. So one can think what it's mean geometry. Like we can feel it in one way.
What if you don't have any x3 in the solution set?
In the simplicial set, you don't have something like this.
X3.
In x3, you don't have anything.
Yes.
You have always, like you have the jersey. Well, how you can't have anything. There is the empty set. There is unique way. Like the empty set is considered as like if all empty is considered as a simple. Yeah, it's considered as a system. No, we don't talking. Yeah, it's also this is compository in yeah, because we yeah, in empty way. No, I will give some example and you will understand. Okay, I think you understood this, like what we in this term of dimension. Okay, let's take the first example, maybe will be the category. Category itself is compository, but when we think about this as a nerve of category, okay? Category is so category and nerve of category is the same for. Okay, so nerve of category, you know what is nerve of category? Yes, you know. Oh, yeah. Look at you. Sorry. Yeah. And nerve of a category.
All the boundaries of for inside of compository, do they
Fill all the
boundaries of axes? I guess in the case of the category, you can fill in boundaries of true simplicity, right?
yeah.
And
Here you can fill all. Yeah. If you have if you have some picture like this, you can fill. Yeah, uniquely. Yeah.
Boundary of higher.
No, the boundary. No. If you have something, I know what you mean. Like if we have something like this, for example, can we fill? Right? No, we are not sure because it depends of this. No.
Right? The right two will have a composition.
Yeah, but what about maybe it's not coincide with this? It not be the same. Yeah. Okay, so what I wanted to show some example, the nerve of example, nerve of small category. Okay, so how it looks like the composition. So it's easy, like of if I have like something in xn, how it looks like. It looks like f1, f2, fn, right? And I have something in xm. It looks like g1, g2, gm, right? This is how it looks like simplex here. But what if they coincide at k, like the end of this, the end k of this, like this ones is equal to this ones. Let's say the last two, fn minus 1, it's equal to this 2, okay? Yeah, let's say it's equal, then I can write like this. I can write f1, f2 until f n minus 2, and then to add this, let's call it's h and k, and this one is h k, because it's coincide when we going like, okay, when we take the end of this one, so h and k, then I add h and k, yeah, and then I add the rest, because h and k I already added, and then I add the rest, start from g3, g4 until gm. And we can see that even the dimension where it will be in, like we added n times m, but we added this 2 twice, yeah, minus 2. This is why it's, yeah, minus k, okay? So we can get, like here, it's, we can get this, but it's too much trivial, right? It's a trivial, it's kind of a trivial composition, like everything we can know from this one, from the, yeah, from how to do this, we can do the rest. Like how to do both two, and we can know the rest, yeah, like this f and this g that coincide at this now it's coincide, then we get this, okay? Okay, two-dimensional, it's the same idea, it's not something, yeah, let's say this is so trivial example, okay? But now the non-trivial example, when we apply on this the distribution, Muna. So this is non-trivial example. Yeah. And how we got this? This is okay. This is example 1, this is example 2. And how we get this really? There is composition there. It's about the we talked about gluing lemma, I think. Okay, let me remind you. Okay, in order to now to define the composition here, I want to remind you something, that if I have something like this on sets, in sets, sorry, A, B, C, okay, in sets, we say that we have, if from, okay, of course we have, like if I am apply here we have the limit of this, the pullback. Of course we have unique, if we apply D on this, D on this, we will get this D cross A, D is a functor, so we will get square. This is square, pullback square, but this is not pullback square. It's not pullback square, but this is the pullback, dA cross dB dC. And of course, because of this tomorphism, it gives me unique dimorphism here, right? Give me unique one here. But actually, this one have a section. I think we talked about this. This one have a section here. So there is always a map from dB cross dA to this kind of a gluing map. We talked about without, like when C is a point. When C is a point, so it's like, okay, what is D of a point? This is only a point, so it's a product. It's only product here, and it's only product here. You remember? We talked like when C is a point, then it's a product, and we talked about this. If you remember, when we did this, the convex category, M, we called it M. You remember? Yeah, so what it's like, it's P, Q here. I have pair of okay, maybe let's write it in the Q here. I have pair, and then P, Q will be distribution on this. So what it's doing, it's send the BA here to the distribution on this product of the distribution of this. This is the product, and we use this, yeah? So this is generalization of this when we have what? When we have here general C, not only C to be one like, you know, this is one element object. I mean, yeah, one element set. But here we need to fix this formula. So we need to fix this formula. How to fix this formula? Let's call it again M. Okay. So like if I have P and Q, like but this P and Q or something here is a pullback. So it's if I down to marginal this to C, it's the same. So it gives me also M PQ, which is sent like BA here, but again BA, remember that BA is BA here. It's something they are coincide also in C. Okay, like if I'm taking these maps, like let's call it F and G, these maps, DF, DG. So it's the same formula actually. P, it's generalized this formula actually. What we have P and this, but we have to divide, which is always 1 here if we divide, but here we divide by df of q, which f of a. Let me explain what that means. Like if we down df of q, q is here. Okay, df of q will be here, and a is here in a. F of a will be here. So df of q is a distribution of this on this. Yeah. Okay, maybe one can ask, okay, why you didn't take G? Like why you didn't did this for G? Why? Because it will be the same, because this P and the pair P and the Q are in here. So if I'm like taking Q or taking P and marginalize this, we will get the same distribution here. And the same by taking A or taking B, they have the same here, GB, and this will be the same. Okay. So really, this one, it's okay. It's no problem with this. Like it's if we take this or this, and this is work. Of course, the first property of this, that really is a section of this. Like if we apply this and then we back, it will be the same. That means like this is kind of composition. Like if we now going and apply, like this is the property. Like if we taking this MAB and apply and down to DP, we can down to DP, all right, by applying the projection here to B and D on this. We will get what we get. What do you think we will get if we apply this projection? Like the projection from this to B, and we apply D of this projection, PR1, let's call it. What do you expect to get if we take P and Q, P in here, that coincide, and we glued them like this new distribution have this formula, and if we apply now the projection on this to B, what we get expected with this P, we will get P. Exactly, we will get P because it's really gluing. Like I have distribution on B and I have distribution on A, but they are two distributions that coincide at C. Yeah. Then but then I made this, but if I'm back to B, like I merge to B, I will get really the Q and P, like what happened there, like yeah, in simplex. So let me maybe in terms of simplicial, maybe if we have, maybe let me give you some example. Like if you have this, you know, like when we have some simplicial distribution, when we have something, let's say simplicial distribution from this to delta zm. Oh, okay, I will do this later. Okay, it's better not to do this now. Okay, I will confuse you, but okay, it's good to understand this, that it's kind of gluing, because if we going here, we will get again P, or if we going to A, we will get again Q. So it's kind of composition or gluing. Okay, you can think about this like this. It have another properties actually, some good property, what really makes we can use like this, allow us to use it in order to prove that this is compository. You can see the proof in the paper. bit long, but let me tell you how really the composition defined there in this one. So what we want now, I want to show you what is the composition on the D of the nerve of C. Okay, let's say we have a nerve of C, and we have here something in this one, M, N, and here K. Of course, that I mean this coming from some pullback like this, like initial and yeah, yeah, like this is as we said before, this is S, the OT, what is called the terminal, and this one is I. Okay. Okay, we have something like this. Then we can go from here using the gluing to here, because actually this I can enter in inside, right? This N can enter, it's the same, right? So I can enter this inside, I can enter this inside, and this inside. So we have here M here. So we can applying M and going to this. Okay, here. We're going to this, and then we know that this is exactly like this. What we say is a trivial one. Yeah, we have here composition like this. So actually, it's trivial because it's the same. Like it's the same. So this actually is exactly equal, or by this, if you want the composition of the nerve, which is trivial, it's exactly nerve of M plus M minus K. Yeah. So this is the composition actually. By using this gluing, this is the composition there. And this composition, you can see it's have some good properties. We will talk about this when I think it's good, we'll talk about this when we will talk about bundle scenarios. But let me maybe tell you some of these properties that can help. Like one of these properties that really low, I will tell one. One of these properties that for this gluing that really give you the associativity. Because by the way, in the definition of compository, you will not find one of the axioms is associativity. You know what I mean by associativity? Like if we take some sigma and composing with sigma 2 that they coincide, and then composing with sigma 3, it will be the same as to compose like this. It's, by the way, it's not, this is something really nice, like it's not one of the axioms, the associativity, but there is a proposition that from the axiom we will get associativity. Yeah, from something called forth and back. So we have actually this forth and back, we have something like this for this glowing. That means that if I have something like this, A, B, C, let's say X, not this distribution, something like this, okay? So we know that I can glue distribution. If I have distribution on this and distribution on this that coincide here, then I get distribution here, right? So what if I'm starting from some distribution on this, some P distribution on this, and some Q distribution on this? I can go here to this, like marginal to this by this map, let's say F. So I can take dF of P, right? And then I will get the distribution on B, right? Then I can glue this and this, right? I can glue this and this. But then I have something here, some distribution here, let's say Q, which is the gluing of this and this. I can glue this, and then I can, by this and this, I can glue them, right? This and this, and get something here, some distribution here. But this will be the same as to glue from the beginning, this and this, yeah? Or if you go in other way, like it's kind of associativity, yeah? There is a kind, so this M have good properties that this M, one of them, this is what make it, you can read the proof, it will be like, this what make like really, it's really compository, and this kind of composition like acting good together, okay, like really composition. Okay, what we need from this compository, actually we want to use it we said for our converse like direction for the theorem we had. So let's back to this. We was talking about this, right? X one dimensional, and this the delta z. So for a while, this is not a nerve, right? This is not a nerve of category, but actually, really, it's a nerve of category. So delta, one of the things that you can see that delta of z 2, for example, if I'm starting, is exactly the nerve of this category, like when I have 0 and 1 as the object, and I have only unique, like from every object to object, I have only unique map. This is a category now, not simplex. Okay, sometimes I'm using it. This is a category. And here, of course, the identity. And here is the identity. Delta of Z3 is the nerve of this category when I have 3 objects, 0, 1, 2, and I have unique map from every object to object, like here unique map, here one map to this, one map from 2 to 1, one map from. Yeah, and of course the identity maps, the one map from 2 to 2, one map from 0 to 0, okay, that's what I mean. And you can continue, like this is in general, delta Z M, it's the nerve of Cm, let's call it. What is Cm? I mean, which have M object, 0 until M minus 1, and there is unique object from every, for every 2 objects, there is unique map. Really, this is the nerve. So that means that this is a compositor. Yeah, this is a compositor. And this what make, okay, so we can like, okay, how we can think about, let's say, one dimensional. Now, for one dimensional we want, of course, we didn't use yet for higher dimensional, which is really, it will be good to think about it. But one dimensional here, we have something like this. One dimensional scenario. And here we have distribution. On this, we have distribution. But we can glue, like if I have distribution here in x1, but they are coincide in x0, then I can fill it by some distribution, right? Using this composer here. Yeah. But actually, what we need, even not this composition, all of this, we will take this composition, but we will take the marginal on this. Okay. So we will define in this some new kind of composition, like coming from this, we need only this, the edge. Like if I have edge, and then we get the distribution on this edge, it's coming from, compose them using the Gluon. It's give you a composition of this, but we take only this one. Okay, so let me scribe it there. Okay, I will go there. It's better. So our composition will be like this. If we have some this to, like here, P and Q to D of delta Z M. But what that mean from this to delta Z M? That means that I have, yes, it's better. What that mean to have something like this in? Let's start from this. What that mean? That mean that I have for this one something on one simplex here. What it's mean in one, like I have some distribution here. Let's call it A. Some distribution here, or P as you want, like P maybe. Yeah, okay. You want it to be P, and here some distribution here Q, where it's here this one inside D of Z M cross Z M, right? Because here this one it's V Zm, yeah, and so on. So we have here one-dimensional one, and one in one-dimensional here. Yeah, that they are here like have the same when I'm going here to Zm by deleting, of course, here by deleting the last one, here by deleting the first one, it will be the same. Yeah. So actually what I have here, P, what it's P, it's like a distribution on Zm cross Zm. We can write it as a matrix, right? Like Zm cross Zm if I'm writing like this. So I can write here like P00, P01, P0, M minus 1, P1, 0. Yeah, we already used this. Yeah? We have something like this, and the Q is something like this Q00, Q01, and such that are marginal here. We talked about this. That means that every column here equal to arrow. The first one equal to this. Okay, we need this in order to compose. And if you back, it will be good exercise if you back to the composition. So this will give you, we know that this will fill here, right? This is the composition, like because it's coincide here. So this will fill here and give me a composition in delta Zm. This is the M of PQ. Okay, M of PQ. And how it's look like, M of PQ? Actually, M of PQ on like IJK, let's say, IJK, like something here, it will be, or ABC, if we didn't use ABC, maybe for this is better, ABC. It will be actually, if you think about it a little bit, it will be P of AB, Q of BC, but we divide by this, the marginal, as we said there. I erase this, like what I said, the df, it will be, so it will be the sum of the one, for example, for A, because we have here B, for B that where they coincide, so it will be B0, B plus B1, B plus, yeah. Yeah, we can do the same. We can do the same for Q, like QB0, QB the sum, but this is the same sum because this is the first column, the first arrow is equal. Okay. Of course, if we have like here, if we are going to the Boolean, like that means that we are working in the positive real, right? Our distribution, but you know what it means, the Boolean, like it's only 0 and 1, our, like, yeah, we can every distribution, like going like this distribution, for example, quarter, half, quarter, 0, we can going by this to the Boolean, that means this. Yeah, if we going to the Boolean, this will be like a product of matrix, like as a product of matrices. Oh, okay, not this. Maybe you can't see now because I didn't do the sum. Okay, sorry. But in the product of matrix, we doing the axis, all right? Okay, let me do something. Okay, sorry. No, I'm hurried to do something. But we want what we said. We want this one, to marginal in this. Now we got this distribution. This MPQ is this distribution. Now our composition, sorry for this, our composition will be this one, like when we margin on this. So we need to take the marginal of this. So this will be the formula of this. It's when we take the sum, because we want to go over all this B. Yeah, we want to go over all this B like this. You can think about this if we taking the marginal of this, like this. So it's like to high this B. It can be anything B. So B going from 0 to m minus 1. Now you can see like this is exactly, seems like, and here of course B0, B until B m minus 1 B. This is the formula, okay? This is the formula, and you see like it's a product of matrices. Yeah, It's a product of matrix if we forget about this. And if we really in the Boolean, it's exactly a product of matrices. Yeah. By the way, this can be zero if one of these zeros, then okay, sorry, if this zero, so one of these will be zero, so it's zero, or both of them will be zero. It's okay, like if this is zero, so it's okay, like no problem. Then it's, yeah, like maybe we have to take some cases like if this zero, but it's okay, because if it's zero, then both of these zero, and then
You
this.
get it from distribution to the volume.
Yeah, from how we go,
Yes.
like you forget about what it's like. Everything not zero, you put one. Sometimes it's good, like it's good. We will show, you can see in the last section of this paper how it's really helped to go to the Boolean, and then life will be easier. Yeah, you can see.
He's asking about the map, right? From
No, he said the map. I don't.
What is the map to go to what?
What's the question?
The original question is the map. Okay. He said that for every non-zero element, we put a one.
Yeah, you go to the Boolean, like you have this distribution. If you have this simplicial distribution, or even only distribution, like simplicial distribution, okay, to D, but D is this D for this, for R positive, actually. Yeah. Yeah. But you can compose with something from here to the Boolean. What it's mean the Boolean? It's coming by, okay, by forgetting, like what we're doing here, like every distribution here, you have some distribution, a distribution that this element give you half, this one quarter, this one like this. If this give you half, so it's one, and so you replace by one. And if it's 0 0, yeah, that's it. Yeah, we have a map, such a map.
Similarly. So there's an underlying map from R every to 0 to B. You're sending a non-negative, non-zero element to 1. 0 goes to 0. So it's like thinking of probabilities as possibilities. If something happens,
If you want,
just say happens, so it's 1.
by the way, D actually distribution, we all the time using this D in order distribution on the reals, like positive reals, right? We're taking only the positive real, but you can define this for every semi-ring. Yeah, you can. And if you have a map from semi-ring to other semi-ring map, then it's give you a map from the monoid. The monoid, it's give you, yeah, it's give you something. So it's give you from drx to dr to dsx. Yeah, a map like this. Yeah, you can think this one if you have such a map by this. Yeah. What?
No.
What homomorphism? Sorry.
R2S is a semi-ring map.
Semi-ring map. Yeah, map between.
It's like a ring homomorphism.
Like ring, yeah.
Yeah, you don't have all the spectra of the ring, but you don't have minuses, right? Okay.
Yeah. What is the distribution? Like, remember that the distribution is only a map from X to R, to this R, such that the sum of them have to be of this, finite number of them. It's non-zero also, yeah. But the sum of them is 1, right? So if you have like this, like if you replace now, okay, instead of R, if you have projection to other, like to the Boolean, then you can replace, like you think that you are in the Boolean. Okay. Yeah, you. Okay. Like everything by pi, yeah. And okay, so this is actually the formula of the composition we have. Okay, this is matrix, like exactly matrix, but we have to divide by this. This is the formula, and this is good when we have one-dimensional. Of course, we have some formula for more for every dimensional, but now we use for one-dimensional. Okay, we use for one-dimensional. If I have here one-dimensional, so we can go by this, we can go. So why is good for us? We can think now about simplicial distribution for one-dimensional as a category. How we can do this? Because we have composition, so we can say the following. We can like let's say I have simplicial distribution on this. This is the shape of the measurement space Let's say this is the shape of the measurement space, something like this, or even here, something like this. My measurement space. Okay. So if I have simplicial distribution on this, what that means? Simplicial distribution. This means distribution, like as we say matrices, like here A, B, C, D, E, F, I don't know, something like this. Yeah. But of course, like every distribution from here to here, we can think about this as distribution from here to here. So we can add some synlex and add here this one and add here A transpose of this. Yeah. Then it's really the same matter, because you know, like the column will be the column will be this, and this will be coincide with this. Like this is the like compatible with this. Yeah, because how we know that this is compatible? We need, because the row it's like this, we need here the column of this to be the sum of the rows is this. But we know that here, because it's the direction it's like this, we know that the row of this equal to the row of this. Yeah. So, but the column will be the row because it's a transpose. Yeah. So we can add first of all for all of them transpose. Like this one will be also here and be transpose, and this same like this are okay. Yeah. And then we can add all the composition, like I can make the composition of this. Like A, here we have D, here this is D actually. This is maybe D transpose. Don't know. D, it's maybe not good. Okay, it's that I don't mean the distribution, but anyway, it's I can compose between this and this and between this and this. If I compose between this and this, so I get some distribution from here to here. And because it's really composition, like the marginal on this will be the same. Like here, if I'm marginal to this, like I restrict myself to the distribution on this, will be the same. Okay. Yeah. So I will get distribution on this. And here, like I will get from here to here distribution. I will get from here to here, like many distribution, all the compositions that I can do. Like from the beginning, we can generate all the composition and get the category. And of course, we will get here. Now, to go to the Boolean, because it's really will be a category, because we have the identity also. Here we don't maybe have really the identity, but anyway, it's category without identity. It's not important. We can add identity some, yeah, everywhere some identity. Like it's not it. But maybe we have money here also. Not all is identity. We have money. What?
What is the composition of A transpose?
Normal, like you A transpose composes. What? Sorry. Yeah, A with A transpose. What is will be the composition?
Yeah.
No, I'm not sure.
So we have to add those two.
What?
Add them to the.
Yeah, you have to add the transpose or everything, and you have to add everything. So you add. Yeah. And you add, and you will get money, other like money. Like here you have money because you can compose, like how you go. You can go like this. You can go like this, compose and get here a map. You can go like this, and then go like this. Many ways in order to get a map here, like some endomorphism, like map from. Yeah.
This is not the free category generated by this graph. This is because we are adding transpose.
Yeah, we added also transpose. Yeah. Like after adding transpose, maybe you can say it's a free after adding transpose also. Yeah. So this is because we have composition and everything work. And what is we have the main theorem that it's this is the main proposition that help to this, that if I think that one is good, no? Or this? No. Yeah. The main proposition that help us, that it means that if I have some p from x to of z2, okay, it's important for z2, X is one-dimensional. And we didn't call what is the category. We call the category like this, CXP. Okay, because it depends on X, on the X, and what is the shape of X and P, right? Of course, M also. I know. No, P. It's including here the distribution. So for every distribution, we have a category like this. And now, maybe this is better, right? This is a good one, yeah. And now this is strongly contextual if and only if there is some X inside X0, like some point, like some object in terms of category, such that, and some distribution in CXP XX, such that this one is strong conceptual. A is strongly conceptual as a simplicial distribution on this, like on a circle, the single circle with delta Z2. Yeah. And here it's easy to know what is strongly conceptual in this. Like, what is this? This like a distribution here, it's only something like this, one matrix, 2 and 2, such as the column is equal to the row, like because it's distribution on this, yeah? So it's something like this, distribution on this. It will be something like, let's say this is called its P. So this will be like, I don't know, X minus P. And this will called also X minus P because it should be the same, yeah. And the sum of this, it will be 1. So P1 minus P minus X plus P minus X plus P. So this will be this one 1 minus 2X plus P, something like this. But anyway, like the one can think about the deterministic. There is two deterministic here, this one and this one. This one, sorry. So the strongly conceptual will be something that not support this, like it should be 0 here and 0 here. This is strongly conceptual. And because the column will be the same as the, so it should be here P and here the same P because it's, yeah, but it's the sum is 1. So this is the only strongly conceptual. Yeah. So it's easy. It's easy. Maybe I can give this as exercise. It's easy to see that this is so if and only if we have this on one, we will get this on one circle. Yeah, this is distribution in one circle. Like if I I will take here, like if I'm take all the product, I can get in some endomorphism this, then it's strongly conceptual. If and only if, yes. Yeah, in the paper I passed the Boolean because it's easier to prove, but there is no, by the way, yeah, this proposition in the Boolean in the paper, but it's true, it's still true, but not in the Boolean, but there it's easier to prove in the Boolean proof, yeah, and then we move to the not Boolean, yeah, but this is still true right here, yeah. So if and only if this is so now we know that okay, we have this some distribution. I want to know if it's strongly conceptual or not. I'm going to the category, make all the computation of the endomorphism. Only for the endomorphism, I take everything that I can get in the endomorphism. And then if I found that this is in some endomorphism, then this is strongly conceptual. If not, then it's not. It's not. Okay, this is the main proposition that lead to the theorem. So why it's lead to the theorem? Because how I can get this in some endomorphism? Because of some circle. Like I take a product of some circle. Yeah, I take a product of some circle, and then it's give me this. But how one can think how we can get this? This is only we can get if we have things like this. The same thing or this only. Yeah, only things like this can give me some circle in the hole that have these things where the number of this is odd number of this. Yeah, because this product with this is the identity, like the plus and minus, like this is minus and this is a plus, something like this. So we need odd number of minus. Yeah, and one can see that really it's exactly what we get from some deterministic that not null homotopic. One can see that this is the same. Yeah, so that what the converse direction is true because of this. From this to move to prove now the whole theorem, it's easy. It's easy. Yeah.
Do we have
What?
equivalent for other ZM?
No, yeah, exactly. No. For ZM, it's not true. I can give example. I didn't wrote. Maybe it's here. But you can find example. It will be good exercise, right? You going to this paper, extremal simplicial distribution. It's started like this. Simplicial distribution. It is a paper of Salman, Cihan, and me. You can find it, okay, on archive, and then you go to the last section, I think, and there is one of the there is one example on 322. Yeah, on 32. No, in 232. There is example. I think the last example there. You will and you can do the whole composition and you will not find any like it's not true, like this is not true, like you will not find, because there is in Z3, yeah, in 3 here, sorry, I think, like what it means Z3 there, the example, and here this one is this K33, yeah, and there is example there. Even you need only this because we move by collapsing to this. You need also to start from this. There is some distribution, and try to take all the composition, or try to. It's easy now to compute. It will be good exercise to compute the end for the end. Yeah, because and you will find that it's not strongly conceptual, any one of them, because in order to be strongly conceptual, it's needed to be zero in all zero in the middle. Yeah. Because again, the deterministic is like this. Yeah, and you will find it's not true there. Yeah, because for some reason, yeah, it's depend to our work now what we doing. Yeah, it's depend. Yeah, exactly. For there is another reason, like for this, it's not only. Yeah, because there is more outcomes. So sometimes.
Okay, questions.
Other questions? Yeah.
I have one. So I think there could be, so the next thing, okay, so I think there are two things to do. One of them is to extend it to higher number of outcomes somehow, right?
No, I see. This is exactly that. For higher number of ways, there is another reason. Like it's not only the homotopy. Yeah,
Okay,
this
okay,
exactly.
yeah.
It's not only the
That would
homotopy.
be
There is another. Yeah, like you
right.
can count the end the endomorphisms here, and it's not strongly conceptual. Like it's okay, but still, it's there is our example in our paper. It's like this. It's good. Like check this paper. It's good to check again. Yeah, this one. Yeah. I'm sure, but yeah, I remember this was maybe the first example that, yeah. But check it again, yeah. This example, this will be good. Yeah, then it's,
Yeah.
but maybe for higher dimension of x, we are not maybe sure, 100% sure about this. Yeah.
Okay, I think the next thing which I don't know if I mentioned that before, we have a conjecture for the, not, this is the cone version, right? The cone with the nerve Z mod 2 as the outcome. And the conjecture is inspired by this result, which, restricts everything down to a circle here. Did we talk about this? The conjecture. Okay, so just can you find contextual distributions or under which conditions you can find contextual distributions on two-dimensional X. There's that mod 2 as the outcome.
Yeah,
So
yeah,
we
yeah,
have a
this
conjecture there.
Yeah, yeah.
And it is very similar to this. Like here you have only one atomic piece, right, which is the circle. So two-dimensional version is similar, but I think this kind of categorical construction can be done for any two-dimensional X, right?
Yeah, but it's a little bit harder to do there. You will have all the composition. You can take the same, like generated by all the composition, but what you get there, it's not really like here, like it's, yeah, like think about, because then you have other kind of composition, like you have suddenly some triangle, and you compose with H, like they have the same point, and you will get pyramid. So for pyramid there is many sides. Which side you will get like this? Like it's okay, but still.
For two dimensions, you can define some sort of graph, right? By replacing the two simplicity by vertices, and then for each edge you can
What replace what? Sorry.
Each two simplex.
Yeah, by
a point node of the graph.
This you know you go to.
Right? So you just take the column, right? Just take the column and then put a vertex for each two simplex. You would get this. Would you get this? Oh no, you wouldn't. You would
No,
get
but this
something
is
dual.
another direction.
No, I think this is like you would get something like a dual graph, right? Then I think, yeah, okay. So what I described the dual of this.
Yeah,
So
it's a good idea to start for example, for 3 to 2, or just 3 observer. You know, like we have suspension like this, 3 to 2, like 3 observers. Then we have triangles there, right? To them. Not with the nerve, with delta Z2, like yeah. Yeah. I let compose and think what will happen. Yeah, maybe.
you will get something higher dimension.
Yeah, yeah, higher dimensional. And
That corresponds to a three-dimensional version. You take one more column.
yeah, yeah.
Okay.
But you don't have, like, it's we can work. It's better now not to take the nerve for this.
Oh yes, that's your suspension stuff up here.
No, it's not use this composition. No, no. But this is another direction. Like, okay, what done there? Maybe we can look and think, what if we compose? Can we get this easier? Like if we using the composition there, I didn't use the composition in this suspension. Yeah, but this, okay, this is one. What I mean, like, let's start with this, because this one we know what is money about these things. So let's start and try to really find how we can compose there. I'm not sure.
Characterization. The other cases, you know nothing.
Yeah, yeah, yeah. Yeah, but it's including many cases, right? It's one dimensional, like it's including many cases. Yeah. Yeah.
Questions? Okay, so let's thank Aziz.
Thank you, guys.
So is this the last part? Finish, right?
Finish, yeah. So next, what we are doing?
Yeah,
yours maybe. Yeah.
I don't know actually, because there could be a change of plans depending on